Okay. 9.2 is gravitational field potential and energy. So this is carrying on from chapter 6, where we talked about the gravitational field strength and the gravitational force. Now gravitational potential energy. From IGCSE, students should remember that near the Earth's surface, the potential energy or gravitational potential energy is considered to be zero at the Earth's surface, and it goes on increasing as the height increases. So let's say this is height h2 and this is height h1, and in moving from here to here, so let's say an object moves from here to here, or maybe independent of the path, if they move from height h2 to h1, the change in potential energy is given by mg h2 minus h1. Okay, so now this works fine near the Earth's surface, but it's not an absolute method of measuring gravitational potential energy. Now fundamentally, gravitational potential energy is defined as zero at infinity. Okay, so this only works near the Earth's surface, because near the Earth's surface the gravitational field strength is approximately constant, okay, for until a certain height above the Earth's surface. But as we go away from the Earth, the gravitational field strength changes, and therefore we cannot consider the potential to be linearly related like that. So fundamentally, potential energy is defined as zero at infinity. Okay, and as we come closer from infinity, closer to the Earth from infinity, the potential energy goes on decreasing. Why? Because gravitational potential energy is basically defined as the amount of work done in moving an object from infinity to a particular point by an external agent. Now, since the force of gravity is attractive, this external agent is going to have to do work basically by applying a force in this direction. So the external force is in this direction, okay, in moving it from here, from infinity to a point which, let's say, is at a distance r from the center of the planet. Okay, so since the force applied and the displacement, let's say displacement are in opposite directions, right? The work done is negative, and therefore the gravitational potential energy is negative. Now, a derivation of this is given on page 9, which leads to a result that the gravitational potential energy at any point in a gravitational field is given by minus gmm over r, where r is the distance from the center of the planet to that point. Now, again, gravitational potential is therefore defined as the amount of work done by an external agent on a unit mass in bringing it from infinity to that point in the field. So that would simply be the gravitational potential energy divided by the mass of the object, which will give you minus gm over r. Okay, so if I have to draw a graph of this, okay, as the potential versus how the radius changes, okay, this is r, okay. Potential versus the distance from the center of a planet, you can see that it's an inverse relationship with r. This should be small r over here, okay. So as an inverse relationship, and it's also negative. So you can see that it's very negative near the radius, near the surface of that planet, okay. And as you go away from the planet, it becomes closer to zero, so less negative. Okay, so this is how you have gravitational potential. Now, if in the next part, in 9.2.3, you have a state and apply the formula relating gravitational field strength to gravitational potential gradient. So if you have, for example, from a point A to a point B in a gravitational field which is pointed in this direction, okay, and let's say this distance here is delta x. Okay. So in moving from A to B, let's say A has a potential of V and B has a potential of V plus delta V. Okay. So in moving from A to B, the gravitational field would have to do work of F delta x. Okay. Now we know that the gravitational force can be approximated to minus mg, because we are moving away from the gravitational field. The force is pointed in this direction, minus mg delta x. Also, the work done by definition is the mass times the potential difference, right? Therefore, we have that the gravitational field strength is equal to the negative of the change in potential difference with the change in displacement, which means that you can get the gravitational field strength from the negative of the gradient of a potential versus displacement graph. Okay, so at the bottom of page 10 you can see that the magnitude of the gravitational field strength at any point in the field can be found by finding the gradient of the Vx graph at that point. Okay? Okay. So you must remember that gravitational field strength here is a vector quantity, whereas gravitational potential is a scalar quantity. Okay? So if I have to calculate the gravitational potential at this point due to both of these masses, I simply have to do an arithmetic addition of the respective potentials due to each of the objects. Okay, so the true potential at this point will be an arithmetic sum of the potential due to body 1 and body 2. But if I have to calculate the gravitational field strength, okay, I have to do a vector addition of the gravitational field strengths due to each of the bodies. Okay. 9.2.5 and 9.2.6 is about equipotential surfaces. So an equipotential surface is a surface at which the potential is the same throughout. So in moving from one point on an equipotential surface to another point, there is zero work done by the gravitational field. Okay, so if you see a body like this, you will see that going radially outwards on a circle with the center as the same as the center of the body, you would have an equipotential surface. Okay, so all these circles are equipotential surfaces. And you should see that the gravitational field lines are pointed radially like that. So therefore you have that the equipotential surfaces are always at right angles to the gravitational field lines. Okay, so if you have, for example, if you see the diagram on page 11, you can see that the equipotential surfaces for two masses are in that pattern, so that the equipotential surfaces are always perpendicular to the gravitational field lines. Okay, 9.2.7 and 9.2.8 is about escape velocity. Now let's see that in a little more detail. Okay, so if there is an object on the surface of the earth of mass m, and I want this object to be able to escape the gravitational field of the earth. Okay, so basically that means I want to get it to infinity. At infinity, the potential energy is defined as 0. on the surface of the earth, the gravitational potential energy of this object is equal to minus g m, which is the mass of the earth, m over re, where re is the radius of the earth. Okay, so now I need to supply enough kinetic energy to this object so that it can overcome this potential gap, right? So the final gravitational potential energy minus the initial gravitational potential energy should be equal to the kinetic energy supplied. Okay, so this means that 0 minus gm em over re equals half m v escape squared, where v escape is the escape velocity. So therefore half m v escape square equals g m e m over re. Okay, so from here you can see that v escape equals 2 gme over re whole under root. Okay, now we know that gme over re square is equal to g naught, which is the gravitational field strength at the Earth's surface. So I can rephrase this as 2 g naught re. Okay, this you can see that the gravitational field strength has a particular value at the Earth's surface, and so does the radius of the Earth, right? So this will yield a value of about 11.2 kilometers per second, which means that if an object were to gain an initial velocity of about 11.2 kilometers per second at the Earth's surface, it should be able to escape the Earth's gravitational field. Now remember that this is an ideal case which ignores the effects of energy loss due to air resistance and other factors as well. So, but in the ideal scenario, this would be the answer. Also, in an exam situation, the students might be asked whether the escape velocity depends on the mass of the Earth, radius of the Earth, or gravitational field strength, and certain combinations of those. So given these two forms of writing escape velocity, the student should know that at any one point of time, given either the gravitational field strength and the radius, or given the mass of the Earth and the radius, are enough to get the escape velocity or to calculate the escape velocity. Okay. Now 9.2.9 is just problem solving involving these concepts, and from there we move on to 9.3, which is electric potential and electric fields.